We've all been there, and we've always wished we could be here. So how do we get from there to here? Flight Plan Management, or FPM, works in concert with the overall Unmanned Traffic Management, or UTM systems, to both deconflict flight paths before urban air mobility vehicles are launched and allow vehicle flights to be safe, automated, efficient, predictable, and precise in both space and time. These advanced capabilities need to be presented in a controlled manner to make them familiar and acceptable to users to achieve public acceptance of urban air mobility overall. There is always resistance to change. The purpose of this session is to understand how flight plan management can provide slow evolutionary changes to move from simple piloted flight to fully autonomous UAM service while minimizing user resistance and building trust and the perception of safety and familiarity. I'm David Russell, CTO of Airio. I started my career developing autorouters for printed circuits and ICs. In fact, I developed the very first PCB autorouter for PCs back in 1980, and I wrote just about every kind of router, including proprietary designs, for 15 years. Since then, I've been researching control system designs for the last 10 years and autonomous systems specifically for the last 5. So it obviously occurred to me that if I could extend my decades of knowledge from 2D autorouters into 3D space, we could apply this as a powerful tool for managing safe UAV and UAM flight paths with all sorts of valuable qualities. A lot of the thinking around managing complex airspaces has been lumped into unmanned traffic management, or UTM. This was our original direction as well, but the deeper we got into thinking about how to build deconflicted flight paths inside a UTM architecture, the more complex and cumbersome it became. That complexity arises because fundamentally, traffic management is really a command and control idea that works for linear systems. But the future of urban air mobility and advanced air mobility in general is not a linear system, it's an exponential one. And exponential systems require a certain amount of autonomy and self-selection to ensure resilience. Exponential systems can scale because they apply the principles of a living ecosystem into the design. So that's what we set out to do. It occurred to us that in the existing paradigm, there are 4 core ecosystem components needed to safely manage multiple vehicles in a shared airspace. We need a traffic management system, or TMS, to coordinate among vehicles in the entire airspace. Varon Vehicles' approach simplifies this requirement by starting their implementation with a TMS system with fixed virtual lanes at predetermined flight levels. This leaves some issues at takeoff, landing, and transitions through the vertiport intersection management areas, or VIMAs. We need mid-flight collision avoidance systems, which involves all of these elements, but mostly it's detect and avoid. Again, this is simplified by creating a closed airspace, but there will always be surprises such as birds, balloons, kites, and uncontrolled hobby planes or drones that could wander into the segregated airspace. This can be solved by watching the airspace carefully with radar systems, or it can be solved by simply designing the system to be tolerant of these incursions. We need an autopilot or other navigational system capable of executing the flight plan within the vehicle. Varon Vehicles simplifies this requirement by utilizing a trained operator on board every vehicle. It is anticipated that the air vehicles will not fly without an onboard operator for some years to come, but that will be dependent on the automation technology, regulation, and user acceptance. Human factors solve additional problems within the TMS and bolster the perception of safety, but they also limit the number of flights and paying customers that can be accommodated. For example, if the TMS flight paths are designed and/or checked by humans, the number and timing of flights is severely limited. If it is automated, correct by construction, and created at the speed of a server farm, the UTM is virtually unlimited. We need a flight path management system for each vehicle that understands the mission, the necessary characteristics of the UAM vehicle, and builds deconfliction into the flight path. This realization that we needed to transform our thinking led us to recognize that what we are facing is not a traffic management problem. This is a flight path design problem. This is the key to scaling, and the reason that we are working with Varon Vehicles to enable system growth beyond the simplistic initial approach. With that understanding, our ultimate goal became designing and developing an automated system that constructs resilient flight paths. A resilient flight path is robust, safe, and stable while operating in a shared space that is highly dynamic and conforms to the set airspace's parameters. Our early simplistic implementations of UAM in Latin America are intentionally structured to reduce these requirements as much as possible. But as the system evolves to handle more traffic at lower prices, and the more Varon vehicle vertiports, the dynamics of the system will continually increase. We are planning for this evolution at the outset. Planning and implementation of the next feature set is being started with the implementation of the initial feature set to allow for expansion of the system. The initial UAM systems will be intentionally simplistic and mostly manual, but we have the technology such that they do not have to be. In terms of scalability, they can't be. The question before us is how to implement these changes and simultaneously drive users' and regulators' acceptance. The core of the resilient flight path system is based on just two components we call AutoPath and the Continuous Path Regulator. The first component is the path routing system itself. AutoPath is an integration of geospatial data, auto-routing algorithms, and big data IT. It runs on a server farm so that it has all of the information it requires to analyze the mission profile, determine and construct the appropriate data sets, vehicle parameters, and cost metrics, and then find and deconflict the path. In the initial Varon Vehicles infrastructure network, this technology will first be used to determine the urban geodesics. Given a list of rules for the geography, land use, and traffic features that are either desirable or undesirable, the system will construct the best urban geodesic path for the links between the Varon Vehicles vertiports. This can incorporate both geographic information systems and new studies about the interactions between autonomous vehicles and people, known as risk calculus. The study of risk calculus focuses on how to create a minimal number of rules and practices for autonomous vehicles to process while providing the maximum safety benefit to the public. The second technology is a new lightweight addition to the flight navigation and control system of the autopilot we call the Continuous Path Regulator, or CPR. The regulator enables the vehicle to fly precisely timed virtual paths where the location of the vehicle is known for every moment of time. This is a prerequisite for deconfliction and will be used to add incremental operator assist features such as cruise control, automated velocity control, lane assist, keeping within the virtual lane and altitude limits, and auto takeoff and landing assist. This presents the features of the system not as autonomous, but in terms familiar and comfortable to regulators and the general public. First, we'll consider the AutoPath system so that we can see how it fits into the overall Varon Vehicles TMS and eventual UTM systems. There are a lot of pieces to this, but today we'll focus on the four core elements. These are the navigation space model, pathfinding and auto-routing algorithms, how we use a geospatial cost function to optimize the path for the mission, and a couple of innovations we developed to support detect and avoid capabilities, something we call avoidance limits and multidimensional trajectories. The navigation space model for Varon Vehicles is a 3D model of the vertiport area, the precise geography of the virtual lane systems, and the vertiport intersection management areas, or VIMAs. In the long run, it is fully capable of modeling a digital twin of the entire low-altitude airspace of cities like Bogota. The auto-routing algorithms will eventually be used to schedule deconflicted paths for takeoff, landing, and VIMA transitions. As flight capabilities evolve, this will become a single end-to-end flight plan in space and time, providing deconfliction at all points and precise timed flights for each vehicle. All of these features can be used to incrementally increase the number of flights possible per hour, maximizing both profits and safety. Cost functions determine the characteristics of the flight path, and as such, these characteristics will be similar for most UAM missions in one city, but can also vary from city to city and even vertiport to vertiport. There may be some differences for different types of vehicles, the number of passengers, and so on, that may cause slight alterations to the basic flight path template. Some of the cost function parameters will be constants, such as distance, while others will vary over time, such as weather forecasts. Each path is not just planned as waypoints. Each path is a continuous mathematical function of position with respect to time. This allows us to plan and know exactly where the vehicle will be at every moment in time, while matching the airspace use restrictions and air vehicle performance parameters. The AutoPath system is capable of identifying the entire fleet of flight paths through the vertiports that are deconflicted with regard to other planned flights. But the planned deconfliction is only as good as the vehicle's execution of the planned flight path, including the essential factor of continuous compliance to its planned position as a function of time. So we need one last core piece. This is the continuous path regulator. CPR is a lightweight set of equations that is an addition to the flight navigation and control system of any autopilot. As some of you may recall from Control Systems 101, most control loops work by sensing an error term. Here's the state of the machine, there's the output we're looking for, change the controls to try to make the error go away. Others may recall the term PID loop. CPR is different. Instead of trying to minimize the error term, it starts with the existing state of the machine, the current time, position, and velocity. There is always some error due to wind, external forces, a bent prop, anything. If we know the desired next state of the machine, we found that it is possible to calculate the exact mathematical simultaneous solution to transition the machine from the initial state to the desired state. The question then is, how do we know what the next machine state is supposed to be? We can know that if we have a trajectory that specifies the exact path and time we want to follow. Aha! That's why we've defined the trajectory as independent dimensions with continuous functions with respect to time. CPR is implemented as two equations. The output of the first equation is a parabola of the velocity for each x, y, and z dimension, which simultaneously solves for the change in velocity and the change in position within the exact sample time. This is not a state estimate. It is an exact mathematical solution. The second equation then executes this velocity profile by converting it to the appropriate flight controls in the vehicle flight control system. The vehicle is now capable of flying a complex, timed path and staying on time, on velocity, and on position for the entire path. This new level of flight precision in space and time changes everything. In our initial Varon Vehicles traffic management system, the initial system concept is to provide a working TMS, vehicles capable of operated flight, and permanently reserved airspaces between vertiports to minimize risk. The onboard air vehicle operators will provide detect and avoid capabilities and fly VFR. In the long term, the commercial viability of the system is dependent on users and regulators' acceptance and low operating cost. These are dependent variables, as low operating costs are only possible with high user acceptance. At the beginning, with onboard operators, user acceptance will be high, but the additional burden of having an operator and the restrictions of simplistic or manual TMS operations also means that operating costs will still be high. Profitability is only provided by profit margins per flight multiplied by the maximum number of flights that can be performed. What we're trying to do with Varon Vehicles is find an evolutionary transition that will lower operating costs and increase the number of flights possible while maintaining user and regulators' acceptance. The basis of user and community fear is the unknown. The opposite, the perception of safety, is based on familiarity and comfort. There will be early adopters who will make informed decisions based on reason rather than emotion, but the majority of potential customers will trust their gut instinct. A good example of this would be to contrast the coming autonomous cars versus cars with driver assist features that have evolved over the last 60 years. The first cars to boast the new cruise control technology were the 1958 Chryslers. By 1960, cruise control was a standard feature on all Cadillacs. Between 1992 and 2017, no fewer than 44 versions of cruise control systems had been introduced. As of now, over 36 advanced driver assist systems have been introduced, and while there is still market resistance to fully autonomous cars, very little resistance has been met by the incremental changes in driver assist technology. Utilizing only the flight path management and CPR systems, we can introduce driver assist features that start simple with fully piloted systems to sufficient features such that the vehicles are essentially autonomous, and we can choose whether or not the pilot is eventually removed. Our goal, however, is not only to make Varon Vehicles users feel comfortable with familiar processes, but to gradually increase the number of flights and vertiports the system can handle to drive profitability and thus viability. Our first example is that of a single link between two potential vertiports in the city of Cartagena, Colombia. The stage between Vertiport Castillo and a vertiport at the international airport. This section is 4 kilometers in length. As currently defined in the initial airspace integration architecture, there are 6 virtual lanes or 6 virtual slots within which we can place a vehicle. One vehicle will launch at a time per virtual lane to guarantee deconfliction. Once the vehicles clear the VIMA, we can continue to launch. In most cases, the throughput of the system is mostly dependent on how long it takes to launch a vehicle and get it through the VIMAs and into its cruise slot. If we assume 120-second window for this transition, we can launch one vehicle every 2 minutes. This gives us a maximum of 300 flights per 10-hour day. Note that these numbers are not intended to be accurate. They are only used to show the relative change in flights per day that may be accomplished under certain conditions. This VIMA is complicated because the straight line path crosses the airport runway. A rule-driven urban geodesic would first drive this lane away from the airport clearance zone. It might then turn south and then turn towards the destination. This would cause higher cost in 2 rules. The first, that it has an extended flight path over people and habitation, and the second is that the large hill in the center of the city is above our altitude limit. A lower cost path is to turn north, then towards the destination, spending as little time as possible over the populated areas. These animations show the flights initiated one at a time through the initial VIMA around to the exit VIMA. Some of the lanes look skewed because they are at staggered altitudes. In the second example, an automated takeoff and landing assist system will automatically deconflict the vehicles as they take off, land, or transition the VIMAs. We can now launch up to the limit of the cruise slot capacity, and the throughput increases to 1,800 flights per day. These animations are simplified to just an entry VIMA connected to an exit VIMA. When virtual lane and altitude control are added, we can now have 3 altitude slots per lane, and the daily throughput climbs to 5,400 flights per day. It is important to note that automating the flight paths through the VIMAs is not only good business, but it becomes a necessity once the number of connections per Varon Vehicles vertiport goes above 2. With these operator assistance additions and flight plan management, a hub and spoke vertiport system design is now possible. With the simple addition of flight path management to the Varon Vehicles TMS system and CPR to the Air Vehicles navigation system, we are now able to provide solutions to the need for scaling beyond the initial simplistic airspace integration architecture into a full UTM system. This provides greater throughput of the system and the key to scaling, precise deconflicted virtual lanes which provide for safer flights, deconflicted paths through the VIMAs, the ability to accommodate numerous flights within the high-traffic segregated airspace for the UAM, intelligent urban planning and design of urban geodesics minimize undesirable impact on the communities. Flight paths are constructed via AI and heuristics to better match the mission profile, payload, vehicle types, weather, and other parameters of importance to the overall Varon Vehicles operations. We're here because we are very eager to collaborate with others in the industry. We'd love to connect if you want to play along with us. There are lots of ways you can plug in. We are looking to collaborate on test projects. We need a few vendors for core subcomponents, especially geospatial data providers. We are in the funding cycle. We are looking to hire a few great engineers, data scientists, and other technical types in the next few months. We need to have some great conversations that can help us think about this stuff deeper, and we would appreciate any moral support along the way. So if you can help with any of these areas, or if you see any areas where we might be able to help you, please don't hesitate to reach out to me at daver@airio.io.